Hey guys, so we're back with number 11-10, last problem for today. This will be our notes on a hypothesis test for matched pairs. This is mu d equals the difference in paired data. So we kind of touched on that in 11-9, like what that would look like. And now we're going to do a problem for notes. It says, Mark loves the carnival game where participants guess the number of jelly beans in a jar and has decided to spend some time practicing so he can win next time. He's come up with 2 different methods for estimating the number of beans. To test his methods, he goes to the thrift store and buys 8 random jars of different shapes, fills them with jelly beans, and tests his methods. His estimates are shown below. Good news, we don't need to write down this table. Is there a significant difference in the number of jelly beans estimated by Mark's 2 different jars for 4 jars like those he used? Provide a statistical justification to support your answer. Okay, so how can I tell that this is a hypothesis test? It's got a question asking if there's a significant difference, which I can answer by either rejecting or failing to reject the null hypothesis, and also they did not give me a confidence level here. So I know I need to go hypothesis test. Okay, identify null hypothesis, alternative hypothesis, alpha, and then mu d equals. We did one like this in number 8, so this shouldn't be too bad. Okay, so what we want to know is there a difference? So our null hypothesis is going to be no difference. And then, as hopefully some of you are suspecting, the alternative hypothesis is a difference, which is not equal to 0. They did not give us an alpha, and this is the mean difference in the number of jelly beans estimated by Mark's 2 different methods. As I'm sitting here, I'm trying to decide how I would do it. I would probably do something lame, like count the bottom and then count the side and multiply it to get how many there would be. Okay, conditions, alright. So, random, independent, and large counts. Okay, so we're going to be really careful here. We've got some stuff going on with our conditions in the last couple problems. It says 8 random jars of different shapes, so okay. Independence. Alright, so the question is there random assignment here? You guys are thinking, okay, it said random jars. This is actually a random sample of jars. So we don't have random assignment of which jar he decided to use which method with, so we're just going to use our usual independence. And we could argue in class whether or not there's 80 different types of shapes of jars, but for now, let's just go with it. Okay, and then notice the large counts condition. We have 8 random jars, which is less than 30, so I'm going to put my little straight line emoji face. I noticed that they didn't give me a graph or anything here, so that is yeah, going to be something I'll have to deal with in a minute. Calculate. Okay, calculate. Okay, notice that they gave us these amounts in the jars, but we need to find the differences. So I am going to line up my 8 jars here. 1, 2, 3, 4, 5, 6, 7, 8. And then I am going to calculate the differences and put them in this table. I'm going to treat this as one sample because it's paired data. So the question is, do I do method A minus method B or method B minus method A? It honestly doesn't matter. I'm going to do B minus A in this problem, but honestly you will get the same answer in the end, because remember, the t-distribution, even though it's not perfectly normal, is still symmetric, so you would just be looking at the other tail, which is no big deal. Okay, so I'm going to do B minus A, which will give me negative 16, 4, no, this is clearly A minus B. Okay, hold on. Negative 16, 4, 2, negative 20. Where's your whiteout, Miss Ide? You're wondering. It's downstairs. And I'm too lazy to go get it. Negative 10. Okay. Alright. Okay. So as fun and interesting as this is, I didn't really give me any information. I need to plug things into my test to calculate. I need things like the mean sample difference. I need things like the sample standard difference to plug in, and I don't have any of that. Haha. So what we're going to do is stat edit, and let me make sure my camera will focus. It's not too bad. Okay, so I'm going to clear out the data from problem 8. Negative 16, 4, 2, negative 20, negative 5, negative 9, negative 6, negative 10. Okay, and I'm going to do stat calc, one variable stats. I'm going to make sure there's nothing in my frequency list because I don't have anything in L2. Okay, so I have negative 7.5 and 8.177. For my mean and sample standard deviation. Okay, and then at this point, what I'm going to do is utilize the information of the 5-number summary to create a box plot so that I can justify my large counts condition. Okay, so I'm going to do this off to this side. I have minimum, quartile 1, median. Oh, you can even tell right there the median and the mean are equal, so this is going to be symmetric enough. But make my graph. Okay. Okay. Alright, so I have a minimum of negative 20. Q1 is negative 13. Median is negative 7.5. Q3 is negative 1.5, and the max is 4. Okay, look at this beauty. -20, negative 13 is 7.5, 1.5, 4. Okay. Negative 1.54. Okay. Box plot shows no extreme skew or outliers. Okay. So just alright. Okay. Now I'm going to do my actual calculate portion. So I'm doing a hypothesis test. T equals, why am I using T? Well, that's because I have sample standard deviation. I have sample information. I don't have any information about the population of estimated jelly beans. Okay, so statistic minus parameter. Remember, parameter is up in the identify portion, over standard deviation of statistic divided by the square root of n. Okay, and this comes out to be negative 2.59, which is great. Okay, p-value equals t-CDF. Okay, so I have a negative here, so I'm going to do negative infinity to negative 2.59, degrees of freedom 7. And that's going to give me 0.018. But remember, I have a two-tailed test up here, so I'm going to take that and multiply it by 2, which gives me 0.036, which is still really good. Conclude. Since our p-value of 0.036 is less than 0.05, we reject the null hypothesis. Okay, so I'm rejecting it. That means that there is a difference in the number of jelly beans estimated by Marks to different methods. One of the methods is clearly better than the other one. Alright, thanks guys. I hope that was helpful. That should get you all the way through paired data. And I'll see you guys on Monday for the next set.